Okay, now that we've talked about the ideal gas law and all the wonderful equations that we can use for it, let's talk about how, well, maybe, kinda, sorta, it doesn't really work all that well. And there are deviations from ideal gas behavior, okay? And so there are certain cases where the ideal gas law breaks down. And when that happens, we have real gases as opposed to ideal gases. So there are a number of reasons why the ideal gas law might break down, okay? First of which is intermolecular forces, okay? One of the postulates of the kinetic molecular theory was that there were no forces of attractions or repulsions between the particles, right? They were just moving independently of each other, and they weren't affected by each other. But that's not true. Attractive forces and repulsive forces do exist, and they might actually be pretty substantial, especially if you have polar molecules where the positive or partially positive part of one might be attracted to the negative or partially negative part of another. Okay, and so that's a problem. The other problem is conditions, right? Extreme temperatures and pressures. If pressures get really, really high and or temperatures get really, really low, okay, then the gases start to behave more like liquids and solids, which are called condensed phases. They get super close together because the pressures are really high, and because the temperature is really low, they're not really moving around. They're just kind of vibrating like this. And so there, we can't ignore these intermolecular forces, okay? So what do you do when all of these things break down? Well, what we're going to do is use something called the van der Waals equation. So let me show you the van der Waals equation. Van der Waals equation tries to take into account differences in volumes and differences in pressure to try to kind of fix the situation. Okay, and so first, let's deal with volume. Okay, if the molecules are in this container and they have a certain sort of movement in the container, it doesn't mean that they can really move around entirely within the container, because if they have a certain size, that volume that they have prohibits them from moving into each other's space, right? They can't just like and kind of engulf another particle. Okay, and so they can only move in the free space between the particles. So if I know how big the particles are and how many of them I have, I can subtract that volume from my total volume to get the actual volume that the gas molecules can move around in. Okay, and so this is going to be the actual volume that is free for the particles to move around. I'm going to subtract the particles' volumes themselves by the number of particles that I have, which is really related to number of moles. So this is going to make the volume smaller, right? Because I'm decreasing V minus NB. So if the volume is smaller, that means that the particles are going to collide with each other more often. And if they collide with each other more often, that means that the pressure should go up. Okay, if the pressure is increasing, I need to take that into account as well. Okay, and so let's think about what it means for things to collide. This sounds kind of crude and vulgar, but it's true. A collision is really two things in the same place at the same time. Okay, and so for them to collide with each other, I have to have two things in the same place at the same time. So for that to happen, I can think about a particle density, right? How many particles do I have in a certain place at that time? So the number of particles that I have in that volume is going to be the number of moles, N, divided by the volume, V. For them to both be there, I have to multiply the particle density of the first thing by the particle density of the second thing. So N over V multiplied by N over V gives me N squared over V squared. So my new pressure is going to be P plus A N squared over V squared. So now if I combine this correction for the volume and this correction for the pressure, which we're going to call the actual pressure, I get the van der Waals equation. P plus A N squared over V squared times V minus NB is equal to nRT. So this would be what I'm going to be using for real gases. And just for comparison's sake, here's PV equals nRT that we were using for ideal gases. Okay, and so the point is that these equations look very similar to each other. Okay, I'm replacing P with this expression in parentheses, P plus A N squared over V squared, and I'm replacing the V with this expression in parentheses, v minus nb. So it gets more complicated when I look at real things versus ideal things. But the van der Waals equation is sort of based on the ideal gas behavior. So just to kind of show you how important these things might be, usually the corrections are pretty small, right? The A and the B are usually pretty tiny, but they can give me better agreement with experimental data, okay? For example, if you consider STP, standard temperature and pressure, 1 mole of an ideal gas has a volume of about 22.4 liters, which, if you want to put things in perspective, is a box about the size of a basketball, okay, about this big. So if the volume is 22.4 liters per mole for an ideal gas, you can see that these B's, which are related to volumes of gas molecules, are really, really small compared to 22.4, right? Much, much less than 22.4. So it's going to be a small correction, but a correction nonetheless. But I can see that as the molecules get bigger, okay, the volumes also get larger, and they start to become more and more substantial, as well as when I go from something that's relatively nonpolar to something that's more polar. Okay, and so for ideal behavior, typically things that are nonpolar and small behave more ideally than things that are nonpolar and big.